Alright, nerds. So now we're going to talk about standard reduction potential. Or, for us, we can actually, if you want to, as long as you remember that it's called standard reduction potential, we are going to shorthand it by calling it E naught. So we call it E naught, and this is one of the calculations we're going to do. It's fairly simple, but we'll get into it. So basically, you want to do two things out of this. You want to undertake calculations involving E naught, so standard reduction potential, reduction Z, we're talking about redox reactions still, and you want to understand what the use of the word standard means there. And it means something very specific, which I'm sure some of you might have guessed by now, but we'll see as we go in. Okay, so standard reduction potential. So total voltage or electromotive force that a galvanic cell or voltaic cell can produce is determined by what we've got taking part in the redox reaction. Okay, so the cell, it says above, it should say, cell to the right, whatever, can be represented as zinc, copper. Now we've seen this before. That's how we write it. Okay, so this and this represents a metal ion couple, and that can be called an analyte couple. NO-lite. So not like, so so it's an analyte couple. The double line represents the salt bridge. We've talked about this before. It's just a bit there to remind you. So here's the thing. The electrode and the electrolyte couples have a fixed voltage. This is a theoretical voltage that really, when it comes down to it, we'll probably never see in an experiment. But this is they have fixed voltage that doesn't change no matter how many moles of each substance is present. They just standard, like that, they've got a fixed voltage, okay? And you'll see that as we go into it. And this actually makes it really easy for us because we can use a table of these voltages, which is what we see in the back of our periodic tables in an exam. We can use a table to predict the energy produced. So the standard reduction potential. This is the term given for the fixed voltage created by specific redox reactions. So what this means is, every pairing, particularly metal displacement, has its own, voltage that it will be able to produce. And it's fixed, it doesn't change. Now, this is where the word standard comes in. It's standard conditions. So 1 mole of solutions, now that shouldn't make a massive difference. It shouldn't change it at all, but still standard conditions. So that's why it says standard. Okay, 1 mole of solution, 25 degrees Celsius, and 100 kilopascals, or 1 atmosphere, whatever, it doesn't matter. 100 kilopascals, 1 atmosphere. So that's what the circle slash. Now, so when we have E naught, we see it as, that actually means standard. That E naught, that part there, the naught, that means standard. Okay, so for example, here we've got zinc, so that this is how it will appear in our tables. You'll see that that's a minus, and copper, so this is zinc reducing and copper reducing. Okay, now over here, what you'll notice is zinc loses electrons, so that's actually oxidation. But over here, we've got a reduction. We'll come back to that. So, well, straight away. So the zinc, as it is reversed, okay, we flip it. Now, this is something you're going to need to be aware of. So, in this case, E equals the copper, which is plus 0.34. Now remember, this is flipped because this is our reduction, standard reduction. This is our oxidation, which is the opposite of reduction, so we flip it, plus 0.76, and this gives us 1.10 volts. Alright, so here we are. So our reaction is that plus that, which gives us a total E naught value. Again, I couldn't quite get that line to go through it with this. So total E value for the cell is 1.1 volts. Alright, that's a very simple calculation, and I hope you've enjoyed the shorter video this time. And yeah, we'll see you in class.